Alright, for this section I want to talk about 12.1, and this is how we apply derivatives. And for 12.1 we're going to talk about local extrema and what those are. So we're going to use derivatives to find behaviors of functions, meaning like increasing, decreasing, constant. We'll talk about critical values and critical points, what those are, and then this term extrema. So the first thing I wanted to discuss, and this is more of a review of what increasing, decreasing, and constant looks like. So increasing, decreasing, and constant always is just referring to the slope of the function. And so this is a representation of the original function, f of x. We always look from left to right. Okay? So if it's going up, it's increasing. If it's going down, meaning the slope is negative, it's decreasing. And then if the slope stays the same, it's constant. Okay? So again, that's just more of a recap from chapter 1 on what increasing, decreasing, and constant looks like for a function. All right. So here are the formal definitions of increasing and decreasing functions. So, just as a reminder, derivative is just a slope. That's all it is. It's the slope of the line or the function, but at any given point. Okay? So you don't have to feel necessary to write all this down. The big thing is just if the derivative is positive, so it's greater than 0, then it's increasing on that interval. If the derivative is negative, so it's less than 0, then it's decreasing. And then if the derivative is equal to 0, then it is constant. Okay? Whether that be at a single point, on an entire interval, whatever the case, but if the derivative is positive, it's increasing. If it's negative, it's decreasing. If it's equal to 0, then it would be constant. Yeah? All right. So now that we know that, let's find an interval on which this function is increasing, it's decreasing, or it could be constant. Okay? So since we're in calculus, as far as chapter 11 and 12, first thing I'm going to do is take a derivative. Okay? So the derivative of this function would be 3x squared. Bring the 3 down, subtract 1 from it. 2 times 3 is 6. 2 minus 1 is 1. And the derivative of 9x is just negative 9. Or the derivative of negative 9x is 9. Okay? At this point, you're going to need... well, actually, before I say that, let me, kind of propose this to you, okay? So, even though I know what the derivative is, I still don't know where it's increasing, where it's decreasing, or when it's constant, okay? But now what I can find, because I know, according to the previous slide, that for it to be constant, the derivative has to be equal to 0. So I can figure that out, okay? So we have a quadratic with 0, or equal to 0. I can factor this, or I can use the quadratic formula. I'm going to factor it, but just to give you the quadratic formula again. If you want to use the quadratic formula, you're welcome to. Okay, but I'm going to factor this. So factoring it says, I'm going to factor out the 3 first. So now I'm looking for things that multiply to give me negative 3, but add together to give me positive 2. So that would be x plus 3 and x minus 1. Yeah. Then I know that each of those need to be equal to 0, so x plus 3 is equal to 0, so x equals negative 3. And x minus 1 is equal to 0, so x would be 1. Okay? So these two values, negative 3 and 1, I know that the value is constant there. Okay. I know that the function slope is constant at -3 and 1. Yeah. Now I'm going to test this and figure out where it's increasing and decreasing. So it was talking about intervals. Well, I know something big happens at -3, and I know something big happens at 1. Okay. So if I look from -infinity to -3, something's going to happen. If I look from -3 to 1, something's going to happen. And then if I look from 1 to positive infinity, okay? I look at my function, and so since I'm talking about a slope here, if I want to know if it's positive or negative, I'm going to look at the derivative. Okay, so I'm looking at the derivative. All right, so what I'm going to do is I'm going to take a big negative and plug it into the derivative function, something between -infinity and -3. Pick your favorite negative number, doesn't matter. All I'm looking for is a sign, okay? So if I take a big negative of, say, -100 million, and I plug it in to this 3x squared derivative, I square that negative, it becomes positive, yeah? So the sign of the function evaluated at whatever I choose between -infinity and -3 is positive. That's all I care about is the sign. Is it going up or down? Okay. Now I'm going to pick something between -3 and 1. So between -3 and 1, the easiest value would be 0. So 3 times 0 squared plus 6 times 0 minus 9, that's negative. Okay. And then I pick out my favorite positive number, something between 1 and infinity. Plug it in, I square it, it's positive, plus a positive, minus a small negative. Okay. So the value of that would be positive. Okay. So what that tells me is I am increasing from -infinity to -3, decreasing from -3 to 1, and increasing from 1 to infinity. Okay. So just to write that down, so I'm increasing from -infinity to -3, and I'm increasing from 1 to infinity. Then I am decreasing from -3 to 1. And I can see that just by the sign. That's all I'm looking for is the sign. It'll tell me if I'm increasing or decreasing, okay, and at what values that sign change happens. Okay? So that would be the increasing and decreasing for this given function. All right. So now, just looking at it graphically, I can see that, what I thought was true, right? -infinity is down here somewhere. So from -infinity all the way up to 3, I'm increasing. When I get to 3 and go down to -1, I'm decreasing, I'm going down. And when I get from 1 and look to infinity, I'm going up. Right? So that's just confirmed what I had just discussed. Okay? Now, all functions, or I won't say all functions, but the functions that we're going to deal with will have critical numbers. Okay? So if a function, or if f is a function, then there's a number c for which f of c is defined. Okay? That the derivative is equal to 0. Okay? So essentially what we did back here, set the derivative equal to 0, solved it, and found that -3 and 1, that -3 and 1 would be my critical numbers. Okay? Or it's also a place that the derivative does not exist when evaluated. Okay? And I'll show you an example of that. All right? So that is the critical number. The critical point is when we take the value that we find, like -3 and 1, and we plug it back into the original function. Okay, that is called a critical point. That gives us the point at which the change happens. Okay, we can see that on the graph. They took -3, plugged it back in, got 31. Plugged 1 in, got -1. That is the critical point where the change happens. Okay? Whatever change it is, that's where the change occurred. And so that is called a critical point. Okay. All right, so now I have local extrema. All right, local extrema is just or extrema is a fancy way of just saying maximum and minimum. Okay. All right, and it has this definition that says that this critical point, if the function is less than the function at the critical point, then there's a local maximum and a local minimum if the function is greater than the function at that point. All right, what that really means, in kind of what we've already discussed in increasing and decreasing, if I have a change from decreasing to increasing, then I have this valley. That is a local min. That's the local minimum. Okay. Now, if I have a change that goes from a maximum to a, redraw that for you here. So if I have a change that goes from a increasing to a decreasing, then that is a local max. That's a peak. Okay. That's what I'm referring to when I say local extrema. Okay. So that's all we're going to look for. Now, the reason it's called local or relative is because it's not an absolute. We don't know that that's the maximum that it is for the entire function, but we do know that at least for what we're looking at, that's a minimum and a maximum, okay? So that's local max and local min. We have a change from decreasing to increasing or increasing to decreasing, okay? That would result in that maximum or minimum. So let's do these. Okay. So I want to find the critical points and the local extrema for the functions. All right, so I have f of x. All right, and I want to find the derivative of a. So I just do the power rule. Go ahead and pause the video and try that derivative on your own. Just make sure that you get it. Okay, so we have 3 times 2 minus 1, so 6x squared minus 6x minus 72. Okay, so that would be the derivative. Find the critical values the same way I did with the first one, except we just didn't know they were called that. I'm going to factor out the 6, and I'm going to set it. Okay, and I want that to equal 0. All right, so now you can use the quadratic formula or you can factor it. So this factored would be equal 0. And so then solve it. So x equals 4. Or x is equal to -3. Okay, so these are the critical numbers, 4 and -3. Now to find the critical points, I can just figure out what f of -3 is. So we'll go back to the original function, plug it in, and I get and so I get f of -3, and that is 150. And then f of 4 is -193. Okay, so the critical points are at -3, 150, and 4, -193. So there's a change that's going to occur at those points. Okay, so now I want to figure out what that change is. Okay. So I'm going to look from -infinity to -3. I'm going to look from -3 to 4. And then I'm going to look from 4 to positive infinity. And I'm going to look at the derivative. Okay. So I pick out my favorite negative number, whatever it is, whatever, as long as it's less than -3, it doesn't matter. I square it. As soon as I see I square it, I know it's positive. Okay? So that's it. I'm plugging it back into the derivative. All right. Pick something between -3 and 4. Well, 0 is the easiest. 6 times 0 squared minus 6 times 0, that's 0. Minus 72, that's negative. Okay. And then I pick out my favorite large positive. I plug it into the derivative. I square it, that becomes a larger positive. So I have positive, then I have negative, and then I have positive. Okay? So I have a max at x is equal to -3. And then I have a minimum at x is equal to 4. And so that would be how you would do A. Now let's look at question B. Okay. So I'm going to take the derivative of that function. Power rule says bring the power down. Subtract 1 from it to make the new power, so 3x squared. To find my critical points, I set it equal to 0. The only value that I could plug in that would make that true would have to be x is 0. So that 0 is my only critical value. Okay. My critical point occurs when I evaluate the original function when x is 0. So I plug 0 back into x cubed. All right. So 0 times 0 times 0, well, that's just 0. So that's my critical point, is at 0, 0. Now I want to figure out if I have any kind of extrema. Okay. I do that by looking on the interval from -infinity to 0. And I'm also going to look at 0 to positive infinity. Okay. If I pick out a big negative and I cube it, or excuse me, if I pick out a big negative and I square it, so I'm checking my derivative. Well, if I take a big negative, square it, it becomes positive, so my sign's positive. If I take a big positive and I square it, the sign's still positive. So I'm increasing and I'm increasing. Okay? There's no extrema that exists because increasing to increasing does not result in a maximum or a minimum. So there is no local max or min. Okay? And this is true because if you look at the graph of x cubed, what happens is it goes to 0. So it comes up, goes to 0, flattens out for just a moment, and then it keeps going. Okay, so there's no local max or min that occurs with this function. All right, and so the last one that I want to talk about is the third one, is C, and so I'm going to take the derivative of it. Derivative of 5 is 0. The derivative of this will bring the power down, multiply by whatever's out front, which is negative 1 technically this time. Then subtract 1, and so that becomes -1/3. Okay, I'm going to rewrite that, since it does have a negative exponent, as this. Okay, so to find my critical points, what we've been doing is setting it equal to 0. Okay, now you kind of have to ask yourself, and you can find this out by graphing it if you so desire. there is no value that would ever make that equal to 0, okay, to find a critical point. However, I can also find the critical point just by referring back to the definition if the function evaluated at that point does not exist. Okay, so I can find something that this derivative does not exist. All right, so the denominator, when it's equal to 0, that will not exist because we can't divide by 0. So the only value that makes that true is x equals 0. So I have a critical value at x is equal to 0. Okay. My critical point I plug 0 into the original function, so I figure out what f of 0 is. It is 5 minus 0, which is just 5. So my critical point occurs at 0, 5. So I still have a critical value because it does not exist. Just because I couldn't set it equal to 0 and solve anything doesn't mean that there's not a critical value. Now I want to find my extrema. So I'm going to look from negative infinity to 0. And I'm going to look from 0 to infinity at the derivative. Okay. So I take a large negative number. I take the cube root of it, right? This is a good time maybe that, just to use a calculator. Okay. So I plug in a large negative number for x. And after it's all said and done, because I have a negative divided by a negative, the sign would be positive. You could plug in negative 100, okay, whatever you want to plug in. And then if I plug in a positive, that means the denominator's positive. I have that negative out front, so it becomes negative. So I'm going to go increasing to decreasing, which means that I have a local max. So I have a max, or local max, at x is equal to 0. Okay? And so that wraps up section 12.1. When we get into 12.3, we'll talk about optimization. But this is the general principle of finding extrema using calculus. And if you have any questions, please let me know.